So our speaker is Steve Shaffer. Prior to becoming an avid curler, Dr. Shaffer received a BS in mechanical engineering and his MS and PhD in materials science and engineering from UC Berkeley. After 23 years in the tribology group at Battelle Memorial Institute, solving practical tribology problems for industry and government, Steve spent 7 years as a lead tribologist at Bruker Nanosources, focused on applications development. He now runs his own consulting company and tribology laboratory. In parallel, he has served the tribology community via participation in ASTM, GO2, and DO2. He is past chairman of the GO2 Committee on Wear and Erosion, and on the steering committee for the Wear Materials Conference. And he was chairman of the Wear Materials Conference for 2009-2011. And he's editor of the SDLE's, an editor of SDLE's Tribology Transaction and for ASTME's Journal of Tribology, and continues to mentor students at universities and grade schools around the US. So thank you, Steve. This should be an interesting talk. So you have control. I'll be at our side.
All right. Thank you, Rob, for that introduction and also for the invitation. You read that stuff. Wow, I'm really busy. I don't know how I got this done. I've wanted to do this for a long time, and it's great that you forced me into it here. So sorry I can't be there in person. Everybody says that, but I guess with the miracle of technology and the internet, I'll be here in electron form. And before I begin, I want to acknowledge that I've stood on the shoulder of giants. A lot of this work has been done by others. And I had a lot of help with my friend, fellow curler and former colleague at Battelle Memorial Institute, Rick Olson. And Rick is the lead ice maker of the Columbus Curling Club, where I learned to curl. And we did some work while I was at Battelle and additional work since then. So with that, I'm going to get us going on our journey and talk about an outline. You always start with that. I'll tell you, I don't think that everybody there, maybe it would be great if everybody watched the Olympics this past February, but I'll tell you a couple slides on the sport of curling so we know why we're interested in this. Any seminar or webinar or lecture I give, I'm going to talk about the 5 tribo elements. Then we'll go on and cover the key concepts the key components, the ice, the stones. There's actually curling shoes and the brooms. There'll be questions, I'm sure, on that. We'll cover why does a stone curl? Big question. And why do people sweep and yell at each other while they're sweeping? Then I'll give some concluding remarks. So that's our roadmap. As a start, some about curling. Curling is a really old sport. Rob asked me yesterday, how long it's been going on. It's been 500 years. It originated in Scotland. And they're typically in the discipline, there's 2 teams of 4 players. They now play a lot of pairs or doubles, but we're going to talk about 4-player curling. And the teams will alternate sliding or delivering these specially prepared stones, they're granite, down a 40-meter sheet of ice. And the deliverer or the thrower, he imparts or she imparts a rotation on the stone upon the release. That's critical. If you don't do that, you get kind of a knuckleball and you don't know where it's going. The stone will curl in the direction of rotation. So a clockwise rotating stone from the deliverer's standpoint will curl to the right, and a counterclockwise stone will curl to the left. There's a couple of basic shots we'll see, and one is called a draw shot. That stops on its own. It's either going to stop in front of the rings or the target area or inside of the rings. And the rings area is known as the house. You'll hear people talk about in the house. The center of the house is called the button. And then the other shot is a hit or a takeout. And in that case, we're going to strike one stone or more than one stone with our delivering stone to reposition them or even knock it out of play. That's usually what they try and do. Sometimes they're just trying to move it to a different position. And the object, of course, like most games, is to score more points than your opponent. And the way you score points in curling is they count up the number of stones of the same color of one team that are either inside or even just touching the rings. And any number of those stones that's closer to the button or the center of the house than the opponent's best stone, you get a point for that stone. So the rings themselves not like target shooting, don't have any value. It's scored quite similar to bocce ball, except in this case, there's no moving target like the little pelotina in bocce ball. this case, the center of the rings is our target. That's called the button. And during the delivery, the non-delivering players, they will sweep or brush the ice in front of the path of the traveling stone of their teammate who's just delivered the stone, in order to make it go further and straighter. It essentially delays the curl. So these are some concepts that we'll get into as we watch a game. So here's hopefully this video works. Okay, so this is a draw shot. And we're going to observe, first of all, you hear that rumbling sound. That's the interaction of the stone with the ice, or the particles on top of the ice. You'll also see how long it takes to travel this distance. You'll see how it's curling more and more as it slows down. We're about 2 feet off the center line now, and almost 3 feet. And we struck another stone and repositioned it a little bit. So that brings up some interesting questions, just watching that. And some of the older curlers may say, gee, I wonder, why does a stone curl? He's probably an engineer. He wants to know why. And this other fellow, the physicist, may say, what is the coefficient of friction between the stone and the ice? And of course, our tribologist colleague recognizes that those are both really good tribology questions, because in the words of Peter Blau, the answer to a tribology question always begins with, that depends. So what can we learn from this? Maybe we can estimate the coefficient of friction between the ice and the bottom of a curling stone. I tried this once, and let's see if we can do it based on first principles. So if you can see my cursor here on the left, I just basically the physics equations of motion for the position of a stone. And the right, we've got Coulomb law, or Antimon's law. I put that in quotes because it is not a law, it's an observation, that F equals mu n, where F is the frictional force acting on the bottom of the stone. Mu is the coefficient of friction between the stone and the ice. N here is the normal force, essentially the weight of the stone. So if I solve this for the acceleration, because what I want to do is get the acceleration out of here, because that's going to show up over here. If I solve, I replace N with mg, the mass times gravity here, and then solve for mu, I get mu equals F over mg. If I replace or know the other physics equation, F equals ma, I solve for A, and I replace mu equals, then replacing F, ma over mg, or A over g. Here's what I get for the coefficient of friction based on first principles from observations of a stone. And so that image where the stone was just delivered, we can take some numbers off of there. The distance is 40 meters. The initial velocity is something on the order of 2 meters per second. And the time it took is about 26 seconds. So we do that calculation, we get mu equals 0.004, pretty close to zero, very, very low. So that's just something to keep in mind of what we might do based on first principles. You can certainly play with these numbers and get different numbers here, but we'll see some measurements later and see where we are. So let's begin our journey on the tribology of curling. If you hear a lecture from me, and I'm sure Rob will tell you this and anybody else, I'm going to tell you that tribology is a system discipline, and that friction and wear are system properties. They're not mechanical properties. There is no such thing as the coefficient of friction or the wear coefficient of Teflon or of ice or of a stone or of steel. It's all about the system. And when I look at a system and I might want to do some experiments, I need to know sort of 5 key tribo elements. And I characterize those as materials, the contact geometry, both macro and micro, the contact stress, the motion, and the environment. So I was trying to see if I can capture those or best estimate or measure those in setting up an experiment or trying to understand a system. So I'll start with materials, the first of the tribo elements. And in curling, we have the ice, the stones, our shoes, and brooms. So I'm going to cover each of those. The ice mostly, stones next, and the others probably just one slide on each. The ice, as we know, or we don't know, but I've experienced this, it should be perfectly level. If it's not level, a stone's going to drift, or what we call fall, in the downhill direction. Usually this occurs when you're playing on what we call arena ice or shared ice. And I'm guessing the closest curling club to you guys is over in Atlanta. There is a curling club there, but they rent ice from the hockey arena, and it's not always level. The Zamboni does some crazy things to it, and the stone won't always travel in the line you expect. It may fall one way or the other. So in dedicated ice, a club that's only used for curling, It is perfectly level because they build the ice by making floods, sequentially laying down maybe 1/10 of an inch at a time, a couple millimeters at a time, and gravity levels that out naturally. And then they do some scraping. And after they scrape, then while it is level, they don't want it to be perfectly flat. And that's kind of surprising. They actually pebble the ice, and it's not pebbles like bits of sand or bits of rock. It's called pebbles, and it's water droplets. They're sprinkled onto the ice, and they form sort of 1 to 2 millimeter size asperities when they freeze. And this is what the stone is riding on. And because of that, the ice contacts the stone only in a very few places. So that's a key thing. What else do we want to know about the ice? Well, the coefficient of friction of the ice versus the stone seems to change with temperature. This has been measured. The ice fracture toughness changes with temperature. And this is a mechanical property that we can measure. The shear strength changes with temperature. The indentation hardness changes with temperature. All these things decrease with increasing temperature. And that's important because we set the temperature of the ice when we're making the ice and keeping the ice house at one temperature, but the sweeping in front of the stone by virtue of friction warms the ice, and therefore we'll see perhaps the result of those changing properties. So how close are we with sweeping to melting the ice? That's a good question. So here is the water phase diagram, and it's just a slice of the pressure, temperature, volume phase diagram. Normally, I think mechanical engineers, we work with pressure and volume. We do the Carnot cycle and those sorts of things. But if I slice it the other way, and I look for water, you look at pressure versus temperature, I see the 3 phases. We got the solid phase in blue, the liquid phase in green, the vapor phase in sort of orange. There's the famous triple point down here. And well below atmospheric pressure, which is this line here, we can go from solid to vapor or sublimation. We can go from liquid to vapor or boiling. So that's this part of the line here. And then from solid to liquid or melting is this part of the curve here. So where are we on the water phase diagram? Where's curling? So because the phase diagram was pressure and temperature, we need to understand the contact pressure and the temperature, contact pressure of the stone on the ice. So for the contact pressure, I need the contact geometry. I ask, what does the bottom of a curling stone look like? What does the curling ice look like? And how do the stone and ice interact? And then the temperature, partly I set it myself, partly it's affected by frictional sweeping. So let's start with the contact pressure. Let's look at the stones up close. The bottom of a stone, if you ever turn one over, is concave, sort of like a dinner plate. So you can see that there's an annular running band. That's this yellow line, yellow dotted line I've shown here. It's about 5 inches in diameter. They vary between 4 and 6, and it's about 6 to 8 millimeters wide. So if I use those dimensions and the fact that a stone weighs about 20 kilograms, I can calculate an apparent contact area here of 0.002 meters squared. I can take force over area. That's easy enough. I can get the force here by taking gravity times the mass, F equals mg, and dividing that by the area, I get about 83 kilopascals. So that's the nominal force if the running band was completely supported by the ice, and that puts us about here. And of course, I'm going to add that. This is an absolute diagram, but that's where 83 kPa is. I would add that to atmosphere, so I'd be just above this line. And again, we're looking at about 0 C, so we're somewhere in this area here between the blue and the green. And the solid liquid interface is pretty vertical at this point. So now we're going to look at the pebble, because now we've looked at the rock, we're going to look at the ice and the pebble. This is what really makes the friction low. It's essentially these are asperities. If I lay down water via droplets, you can see here's the pebble head, and by shaking this back and forth, we can splash this onto the ice. They'll freeze. And when you do it time and again, it kind of looks like the surface of an orange. In fact, this is pebble and this is an orange. So they do really look like one another. And the result of that is that the real area of contact under the running band is likely very small, because we're only sitting on bits of pebble on bits of running band. So let's recalculate now. If we take the running band and the pebble, the stone's riding on just a few of the asperities, it's a much greater contact pressure. We did some measurements at Battelle. This is pretty easy. We took some carbon paper, put a stone down on it on top of the ice, and then we got a picture in it and digitized that. And we ended up with an area an two orders of magnitude smaller, 0.0005 square meters. And our colleagues over in Sweden at Uppsala, they did some Fuji, or I don't know if they used Fuji, they used some pressure sensitive film, and they found that the contact spots was about 1% of the sliding band. And this number here is about 2% of the 0002 we measured before. So we're in the same ballpark. And when we use those numbers, now we're at about 4 megapascals. So now we're way up here on the curve for the actual stone pressure on each asperity contact. And if we blow that up, we start looking at the temperature. Let's now find out where we are. When we're making ice in a curling club, we want to set it, and we find the ideal temperature is about -4.5 C. So below zero, obviously it's got to be freezing. But if we make it colder than that, it seems to decrease the amount of curl we get. And that's because certainly the best current theory, which I'll show you in a minute, says that the stones curl because the front part of the stones, of the rotating stone's running band, is going to scratch the pebble at a mild angle as the stone rotates. If it rotates too fast, it's a very steep angle. If it rotates slowly, it's a mild angle. And the asperities on the trailing part of the running band, they catch in those grooves, in those scratches, and this imparts a small force vector laterally, pushing the stone sideways. So the ice needs to be soft enough to scratch, but not so soft that the frictional contact wears the pebble down after 1 or 2 passes of the stone. And in fact, you'll see this change over the course of a game, that the amount of curl changes and the speed of the stone changes because the pebble is being worn down after repeated contacts. So what we observe is if we warm the ice from that -4.5, if it gets up to about 3.8 or higher, the pebble is soft and it really wears down from the contact of the stone on the ice, it just wears down too quickly. If we go lower, not much lower, at -5 degrees, we don't see as much curl. So we need to be pretty close to, but not too near, the solid liquid boundary. So here's our optimum curling conditions shown right there. Notice the curve is quite vertical there. And if I blow this up, here's our curling conditions optimally, -4.5 C. We're at a pressure of about 3.8, let's call it 4 megapascals. And what we observe is that large changes in pressure, because the line is vertical here, large changes in pressure really don't get us closer or further, not much, from the solid liquid interface line. However, small changes in temperature, 2 degrees, 3 degrees or so, they really rapidly move you to or from the liquid boundary. So one question is, as we sweep in front of the ice and cause frictional heating, can we move it across this and actually get into the liquid zone? One of the models says there is a thin liquid film brought from the front to the back of the stone, and the difference in friction is what causes the stone to curl. So here's the effect of temperature. This is a video. Oh, let's go back up. Sorry.
It's one of the first things that blew out of the water. Yeah.
The University of Western Ontario has been conducting top secret research for the past 2 years into what happens when curlers sweep. It's all part of an effort to put Canadians on the Olympic podium.
It was commonly held that when you sweep, you're melting the top layer of the ice and making a lubricating water layer. Nobody's melting anything. And even the best sweepers in the world, and we looked at some sweepers who were built like linebackers and absolutely pounding the ice, they got it up to maybe -1.
So he's very confident based on that sort of macroscopic infrared view that we're not melting the ice. Now, you can argue maybe at a micro level or at a molecular level, there's a thin film of melted ice into water. Hard to say, but those experiments they did, and the best they could get was still, they weren't melting it on a macro level. They were getting to -1. We don't raise it that much. Certainly, I'm not that good a sweeper. I don't raise it very much at all. But we're warming the ice, but clearly that is going to affect its properties. So from the literature, we can grab all kinds of things, and these are the folks who study glaciers and cold regions and that sort of things. So here's a plot of the tensile strength versus temperature, and again in Kelvin 277 or whatever 273. Here's our melting temperature, and as you get warmer, in other words, from very frozen up towards the melting point or freezing point, you decrease the tensile strength. Same thing with the shear strength, and that's just more circles. Shear strength and tensile strength are related, but these are two different studies. People did indentation studies with an indenter into ice, and those are physicists, and they saw the same thing. As you get warmer, as you get close to zero, and I don't know why this dropped down here, but as you get close to zero, your penetration hardness decreases. And interestingly, same thing with your fracture toughness. And I would think that might be the opposite. As I got a little softer or more ductile, I would think my fracture toughness would increase, but that's not what they observe. So all of those four factors decrease as the stone gets closer to the melting point. So if we put brooms and sweeping together, how do we use those in a game? Well, the broom is generating friction, certainly, and it's warming the ice in front of the stone, and it's changing those flow stress and fracture properties, as we just saw in the previous two slides. It also somewhat polishes the asperities on the ice surface. And here's, again, some work out of Uppsala, where this is a profilometry profile of a stone and the ice after it's been crossed by the stone. I don't know if these two go together. They put them together in their figure. And here's a pebble, an individual pebble, that after sweeping, and it's quite smooth. But what this means is, as the stone went across that pebble, it knocked chips of it off. And we see this at the end of a game when we mop the ice up with a big string mop. You get lots of snow. Well, not lots of snow. You get snow coming up because we've broken down the bits of pebble. So this is what happens. We're polishing it, which makes it break down a little less, and the stones glide over it. But we're also breaking off the tips as well and digging into it and scratching it. So the general trend we saw in those slides is, as we warm the ice, it becomes easier for the asperities on the stone to deform the ice, to plow through it or indent it, and to fracture small pieces off of it, because our fracture toughness went down as the stone warmed up. So we're helping to all those things to be accomplished as we sweep the ice. Let me move on to the materials now. This is the materials number 2 is the stones. The granite for the curling stones comes from one geologic formation in the world, and that's over in Scotland. There's an island called Ilse Craig, and further down in Wales, it comes to the surface. They're able to get it, and there's kind of two different types of granite. One is called, I think there's red Trevor and blue hone, and one's better for the running band and one's better for the striking band. And most modern stones have an insert in the bottom of the one type, and the rest of the stone is of the other type. And that's nice, because then these inserts can be changed to give the stones a longer lifetime. A typical curling stone will last 50 to 100 years in a curling club. You do have to sand them. You do have to texture the bottoms every season, or maybe a couple times a season, depending on how they're performing. But the stones, this granite is so nice, and other granite just doesn't work for curling because it's got a very high fracture toughness. It's got a high coefficient of restitution, so you have nearly perfectly elastic collisions when the stones strike one another. It has extremely low porosity, and it's hydrophobic, so there's no water uptake. So it's not going to have this freeze-thaw cycle, and which brings mountains down to grains of sand eventually. Those are the really good properties of this type of granite. And here we see the striking band, and it's an inch wide or so. It can be plus or minus that. And it's roughly ground, and that gives the stone some grip when they collide. It also cushions it a little bit. It turns out that if they're very polished, the collisions are too elastic, and the game changes in that case. The bottom of the stone, as we saw, is machined to be concave here. And the running band, again, is 6 to 8 millimeters wide, and it's finer ground, not super fine, finer than the striking band for sure, but it's ground with, say, 80 to 100 grit paper. And then there's a plastic handle they mount on top. There's a through hole and a bolt that comes up through the bottom that's in this countersunk hole here. The third material are curling shoes. You have two shoes. You have a sliding shoe, as you saw in the first video. You're sliding out with one foot, you're squatting on that one, and the other foot's trailing behind you. The sliding shoe's got either Teflon, most shoes have Teflon on the bottom, or the really good curlers may have stainless steel pads on them. These are either pads or disc, and the coefficient of friction is very low, 0.005, sort of on the order of what we saw for the stone and the ice. The trailing leg, on the other hand, has a gripper. It's made of crepe rubber. You can see those here. And that has a much higher coefficient of friction, like 0.5. And that's so we can get up and down the ice without killing ourselves. Although the really good curlers or experienced curlers, you'll see them sort of skating, and they're just pushing with the gripper foot and just sliding on their Teflon foot. And the other thing with the shoe is you can see here it's dipped in epoxy, and that gives you a sort of also a low coefficient of friction, so it's not dragging. If you're not good enough to keep your toe off the ground, it's hard enough to keep your knee off the ground. You want to minimize the drag so that you can slide as consistently as possible and as far as possible, so that when you release the stone during your slide, and you're always slowing down, the point at which you release the stone is what controls the distance it travels on draw shots. And usually on the shoes, they're insulated. They're usually made of leather or some other insulating material, A, to keep your feet warm, but B, so you don't transfer your heat down into the ice and melt the ice during play, because that would melt the pebble off. The fourth material is the brooms. The old brooms in the old days were made of corn, and you sort of slapped the ice, and they were just basically clearing debris off of it. They really weren't warming it, as far as I can tell. I don't believe much. So then we came with bristle brooms, and those are made of horsehair. And today, most all the brooms or brushes are coarse nylon fabric, foam behind them, and sometimes they're ribbed. And here's a high mag photo of one of these pads. You can see the ribs here. You can see that the asperities or the nylon weave is on the order of 1/2 to 1 millimeter or so in one direction, and maybe 1 millimeter or so in 1 to 2 in the other direction. So that's the modern curling brush. And there was actually a controversy some years ago. In 2013, the work following up on Nyberg's work on why does a stone curl, research was done to put forth a new theory, the scratch guiding theory. So that was done in 2013. So that's the prior. In 2015, people who watched this and understood it said, hey, we can reverse engineer this based on this theory. And if we make broom heads that could, change the nature of curl, causing it to even move in the opposite direction, we would have an advantage over the other team. So these broom heads, they had sort of directional fabric, a very aggressive surface, which could scratch the ice. And they also had a heat reflective backing behind this fabric, which could excessively warm the ice. So they were trying to soften it and scratch it, and that would affect the direction of curl much more so than any natural sort of thing. So it became sort of unfair. There was a lot of discussion in the curling community, and there is a World Curling Federation. And upon review and consideration of the data, good for them, they banned such broom heads for use in high-level competition. They wanted the athletes to determine the outcome and not the equipment. So let's cover now the rest of the 5 tribal elements. That was all materials. The contact geometry, we mostly covered that. The macro geometry is flat on flat, conformal is what I call it. And that's the 6 to 8 millimeter wide annular ring on the stone. And the micro are these asperities, or the pebble on the stone. We saw images of that. And that's due to the sanding pattern on the stone and the asperities on the ice. The contact stress we saw was about 4 megapascals locally. The motion, easy, is unidirectional, which is a combined longitudinal and rotational velocity. And we'll get into this, but on one side of the stone in the direction it's curling, let's say it's curling clockwise, the left side I'm adding the rotational velocity, and the right side I'm subtracting the rotational velocity. But it's on the order of a handful, single digit meters per second. And the environment is sort of -5 to -2 degrees C, depending on the starting ice temperature and the effectiveness of the sweepers. And it's under ambient conditions. I put ambient in quotes there because most curling clubs usually only operate in the winter, and they don't have a dehumidifier in their club. Some of the clubs that operate year round, or if you're in the Midwest, not up in the north, you will have a dehumidifier, and humidity is really what I call the enemy of the people. It creates frost. Water, of course, we know below the dew point will condense on the coldest surface. Well, that's our ice. And so we get frost on the ice, and this has a tremendous effect. It really reduces the stone's speed and the distance traveled, and requires significantly more sweeping effort. And if you're playing in a club and you're throwing most of your shots down the left side or down the middle, and sort of towards the end of a game or end of an end, you need to throw on the right, and it hasn't been swept or traveled by a stone, and is frosty, it's going to be a completely different type of shot. You need to put a lot more on that stone before the release in order to get it down there. So this is something it really changes the game. So really don't like it a lot. And all of the Olympic events and world events are in an arena that has dehumidification. And it amazes me that with 5 or 6 or 8,000 or 20,000 people in an arena breathing, they can control the humidity that well. So I admire the ice teams. They're doing it right. Our second question, why does a stone curl? Let's address that. Well, here's what we observed. A smoothly polished stone, and I mean 400 grit, 600 grit on that running band, it doesn't curl really hardly at all. A roughened stone, so now we're talking 80 to 120 grit, that will curl. The stone curls more as it slows down. If it's going fast, it doesn't curl very much. We see this in a takeout. If I throw a spinner, in other words, a stone that's really rapidly rotating, it doesn't curl much. We know the ice temperature affects the amount of curl. And as I mentioned, the curl changes over the course of the game as the pebble gets worn down with successive stones traveling down the same track. There are different theories here. There's a differential side-to-side speed. We talked about the rotational velocity being added or subtracted to the translational velocity on opposite sides. There are some differential friction theories, front to back instead of side to side. There's a wet friction and a dry friction theory. There's some pivoting on contact points, sort of a torque-based theory. And there's the scratch guiding theory. And I certainly don't have time in this short seminar to go into all these in detail, but I'll give you some references and you can look those up if you like. What is the basis for the side-to-side velocity theory? Well, you remember my calculation, way up at the beginning, maybe slide 5, we got 0.0005, close to 0. And actually, you can do an experiment. You could take a motor and a force sensor and a frictionless pulley, pull stones at different velocities. You can then plot the coefficient of friction divided by against the sliding speed. And two things in this graph. One is that a polished stone at high sliding speed, even down to low sliding speed, near 0, it's around 0.01. So that's maybe an order of magnitude higher than what I calculated, but that was based on a constant acceleration or deceleration, and we know that that changes as it goes down the ice. And a scratch stone, and this is why we see them curl, the coefficient of friction changes, it increases as you get down towards 0 velocity. And we could see that we observed this in curling and on that first video, that the slower a stone is going, the more it curls, and the coefficient of friction at the same time is going up. So the differential velocity, if we have an advancing side versus a retreating side. So here's the velocity of the angular velocity, sorry, the linear velocity of the stone is this. On the one side, up the top, the retreating side here for this counterclockwise rotating stone is subtracted. It's added on this side. So here's the two velocity differences. We think, well, that should make a difference. If I steer a tractor by braking the left side, it's going to turn left. And so, you know, left-right braking works to steer a tractor. But in fact, if you do the equations here, the left-right velocity difference leading to a friction difference, it doesn't put any lateral force on the difference of a stone. It's just a torque. It's in the longitudinal direction. So that really, even though it sounded good to me initially, does not account for the curl of a stone. Then there are these different front to back theories, and there's a treasure trove of articles. If you look in the Canadian Journal of Physics by these two authors, Shigelski and Denny, they've been at it for a long time, at each other for a long time. With there's sort of the wet friction model of Shigelski, where he says a thin film of water is dragged under the stone. More recently, he's got the pivot slide model. And then you've got the snowplow or the dry friction model of Denny, where ice particles, and we saw they're broken off. There definitely are ice particles get dragged under the stone, and therefore it's ice friction and not ice stone friction. There's lots of debate that goes on here, and it may be that there's some contribution from all of these. I leave it to you guys to get these papers and read them for yourself. But the scratch guiding theory, the scratch guiding model, is really the one I believe in. So if you recall our first two observations, that a smoothly polished stone doesn't curl and a roughened stone does curl, and here's how they get the roughness on there.
Running the top and bottom over coarse sandpaper gives the stone more traction on ice.
That's it. And we do these in the club and measure measure that, or put a roughness on them. We've also done some experiments where we've measured the roughness and tried to do some curling. We weren't consistent enough in our delivery that we were good enough. We're looking for that stone delivering machine. You mechanical engineers who need a senior project, that would be great. So here's the scratch guiding theory. So here's a stone traveling to the right with it rotating in a clockwise manner, and these lines you see here are the scratches that would be left by these 4 points on the running band. And as the stone moves forward, those scratches, are in the ice like this. And so here we are just before, that's the projected path. And as the back edge of the running band comes along, it's got scratches, and these are coming up, and they interact, at least this one and this one, with the initial scratches, and they fall off the front edge, they crash into the back edge, and that imparts a very tiny lateral force by these asperities on the rear edge of the running band, hitting the previously made scratches, and moves the stone sideways in the direction it's spinning. So here's an experiment. Again, our colleagues at Uppsala, you'll hear a little bit of Swedish. I don't know what they're saying, but I think he's saying, ready, I'm going to go. They've pre-scratched the ice, and here's a broom they've just laid down to show the line of demarcation. They scratched the ice a chevron pattern in one direction. On the other side of the broom, it's in the other direction. And the 2 experiments we're going to see are a polished stone, which recall doesn't curl very much, and a scratched stone. And so they're, in the case of the scratch stone, it's going to interact with these pre-scratched ice. And this is, by the way, how they reverse engineered the other teams to make the brooms such that they could scratch the ice and change the direction of curl. So here's our first experiment, and this is a smooth stone being pushed down the ice with no handle. When I say no handle, obviously I can see the handle, that means no spin on it.
Och nu samma experiment med den polerade stenen. Kommer Harald.
So straight down the ice, smooth. We can see it's crossed over. It's starting to develop a little bit of a handle, but not much curl at all. It really doesn't travel off the center line at all in that one. So that was the smooth stone. So the roughened stone is coming up. So this has the bottom polished at 100 grit. It's moving to the right, it crosses the broom, it interacts with the other scratched ice, it moves back to the left, crosses the center line with a tremendous amount of curl at the end. So I was convinced this is the theory, this is the major mechanism that's working. The others may be contributing, but that to me is why it happens. So that's kind of my introduction. I want you guys to think about it. I'll show you some actual curling action here to get you excited about the sport. So these are videos from some Olympic action. This is a double takeout. And what I mean by that is that it's going to, so there's yellow stone. So right now, red, they're leading the game 6-2 at this point in the game. And they're sitting with the number 1 and 3 stone in the house. That means the stone that's closest to the button is this red one. That's the number 1 stone. The number 2 stone is this yellow stone. And the number 3 stone is this red. And the number 4 is this yellow. And that's the number 5 stone of stones in the house. So yellow has the last rock. They're going to be delivering this rock here. It's called the hammer. They're currently sitting number 2, and they're trying to hit this red number 1 in just the right spot to knock it out over here, roll over or carom over, and hit this other red out between this port. And if they don't go out themselves, they jam on this stone or they sit, they will sit 3 and bring the score up to 6-5. They're much more in the game than 6-2. If they hit it on the nose and knock it straight out here, red gets a point, and then it's 7-2, and they're pretty much out of the game. So let's see what happens here. Loading the video.
Boy, they pounded that all the way down. We're sitting right behind the sheet. It looked to me like it was going to curl across the face. And here's the double.
So they're trying for this double.
Just like that. If he hits half a rock, he's going to make it, score 3.
Half a rock means he wants to hit it on the right-hand side and not nose the rock.
U.S. looking for a little bit of a break here. If David Murdoch hits it on the nose, they're only going to get 1.
So U.S. is hoping he misses a shot and hits it on the nose.
Save his shooter. Absolutely. The hammer is en route. Big weight. Oh, he's got a beauty. He's got a great shot.
A long three. Back in the chase for the bronze is David Murdoch.
So that's a double takeout. We can do that once in a while in our club. Triple takeout you hardly ever see. So in this case, yellow, previously they had a guard out in front of the house. Now it's in their way. They need to just squeak by it. They need to hit the front red stone into the other two red stones that are sitting in the middle of the rings to try and take them all out. And again, I have a little loading delay, but we're almost done. I think I'm getting us back on schedule here to 9:30. Okay.
Because they can come into the intern side now.
So here's that redstone, redstone, redstone.
Yeah, they're going to run. This may be their chance to get out of this jackpot they're in.
They try to get by this yellow
He has to
stone
make contact
and hit
with
that
those
red
two on the
stone to
forefoot.
knock those two out.
If he gets what he can see, he'll make it.
Just by. Takes all the reds out.
Is that any good?
So I don't know if that doesn't get you excited. You probably aren't much of a spectator. So I have some concluding remarks, just a couple of slides, and then I'll be ready for questions here. So first of all, thank you guys for tuning in. If you're sitting in the room, you didn't have a choice. Curling certainly is a sport of tribology, and as a tribologist, one would think I'd be a better curler, but I enjoy the heck out of it, and I am getting better now after 16 years of doing it. And what I appreciate is that the governing bodies of curling have used objective data from the scientific and engineering community to modify the rules. In other words, they outlawed the brooms, which can reverse the natural curl of a stone, the way it wants to curl because of the spin, to permit the athletes to determine the winner of the game and not the equipment. I think that's great. Of course, there are many thought-provoking theories and models regarding why a stone curls. Likely there are multiple mechanisms operating, some stronger than others. This is often the case in tribology. And in my opinion, it's the interaction between the asperities on the stone running band and the pebble on the ice. In other words, the scratch guiding theory, that's the dominant mechanism. We saw that polished stones really don't curl. Roughened stones do curl. And that seems to do it. If you pre-scratch the ice, you can make it curl more or even reverse the direction depending on the direction of the scratches. So I encourage you all to go to your local curling club. I'm not sure in Auburn where there's a closer one. I know they've got a club in Atlanta, and give it a try. And at this point, I'm happy to try to answer any questions as time allows. And Rob, thank you again for the invite.
Thank you, Steve. Very interesting talk. They might have curling in Columbus, Georgia. I know they have hockey there.
Yeah, but they may be able to rent the ice. All you need is a bunch of Canadians living, expats living in a city, and they'll try and find a place so they can curl again. But typically they'll rent the ice, and hockey seems to have better priority. So we usually get it like Tuesday nights at 9:30 to 11:30. And then with the obligatory socializing and beer drinking afterwards, we're not out of there till well after midnight. So yeah, don't ask me important questions on Wednesday mornings usually, because I'm up late on Tuesday nights.
Anybody have any questions?
I got two quick ones.
Okay.
One, I'm assuming there is some sort of grand strategy behind these guard stones to try to cut down or block off the opponent, right?
Yes.
Am I understanding that right?
That is correct. And I'll share something with you. About 25 years ago, so there is a rule in curling that those guard stones, the first 4 stones, now it's actually the first 5 stones in an end, the first 5 stones delivered, if they're in front of the house and in a guard position, the other team is not allowed to knock them out. And that does now provide some strategy where typically you'll set up a guard stone and then you'll put stones behind it later in the end, which makes it hard for the other team to get them. First, they have to knock the guard away, and they're not allowed to do that the first 5 stones. So that's exactly the strategy. You hit it on the head, that you can put stones behind it. The really good curlers will use a front stone, a guard stone, to knock another stone out, but you have to hit it so precisely within a millimeter or two to, especially if it's a high guard, to send it back into the other stone. But that is part of the game now. It makes it much more interesting. Previously, without the free guard zone rule, one team would put a stone in, the other team would knock it out, first team would knock it out, back and forth, 1 point at the end of the end. Pretty boring game to watch. So it is part of the strategy, and it makes it a much more interesting and exciting to watch sport. Great question. How about number 2?
My other question was with regard to the illegal broom design. I assume by the fact that the organization actually banned it, that the documented evidence, the testing showed a dramatic change. I mean, when we talk about changing the direction, it was so overt, it was undeniable.
Yeah, well, you saw it. You saw it when they scratched the ice previously with sandpaper. And so now they're doing it with the brooms. It was. You can actually still get brooms that'll affect the curl. You can use them in your own club. All of the ones used in the world and Olympic level, they have a serial number on the fabric and on the broom head so that we know they're legal. So even though it's an illegal broom or an outlawed broom, people still have them. So yeah, the evidence is there. And if you're a good sweeper, you can make it curl more or decrease the curl.
Thank you.
Yep.
Any other questions? On the other side, are all the stones the same, or, could someone strategize and use certain stones at the beginning, at the end, or?
Not necessarily. Well, Rob, that's another really good question. People who play in their club or different clubs, people who play the sport a lot and go to dedicated ice clubs, they'll have a stone book and they'll keep track. And so the, red and yellow or red and blue, or whatever the stone colors are, there are 8 of them, and they have a number, on sheet 2, because the stones live, they stay on the sheet 1, 2, 3, 4, 5, 6, 7, 8, however many sheets your club has. My old club in Columbus had 3 sheets. So 1, 2, and 3. And they keep, stone number 7, blue on sheet 2, didn't curl as much. And of course, each time they sand them, that'll change. You can't, I think you can change in a game if you notice. So what happens is in the first few ends, you'll start to observe if you don't have a stone book or send your, all teams are 4 players, but they have a 5th alternate. And their job is to actually go out the day and the night before and run all the stones and try and match stones. Because what you want for your skip, the last person who throws, if he throws or she throws a stone and it curls a certain amount, and they expect the next stone to behave the same so they can position their broom, a little bit over, because we need to hit this stone right exactly here. And those stones are quite different. They're not matched. That's a big problem. So the stones are supposed to be matched. They aren't always matched. People can keep track of that over the course of a game, or even before the games, over the course of several games with a rock book. And that is part of the strategy. They may say, hey, the skip says, I need a stone that curls more. And if they aren't matched, the ones you see in the Olympics, those are very expensive, very well prepared stones. But in a club, you may say, hey, the number 2 stone, it curls more. So the skip may say in the last end, I need this to curl a lot, or I want to curl more. I want to throw the number 7 and 2, and my lead is going to throw number 1 and 8. So great question. I only recently have started to look for that. What you can do is push one stone with another stone and then stop. If they separate, the front stone is faster. If then you reverse them and you push them and they don't separate, that confirms that. But in order to see how much one curls versus another, you need to be a very consistent thrower in order to see those subtle differences. And the answer to your question is yes, they do vary. No, you can't change. Once the stone has been thrown, that's it. It's used in that end. But as the ends progress, and you've noticed one stone is always a cutter, curls a lot more, you'll give that to the lead. You don't want the skip to be throwing a stone that he can't predict where it's going to go. So excellent question. And yes, we do observe that.
Any other questions here?
Yeah.
I have one more question, and maybe I'm trying to make a point too. If I understood correctly, the rougher ice with the pebbling had less friction, lower friction than like if you had a very smooth ice.
No, the rough and smooth was on the stone. No, I'm sorry, I may have misspoken.
Well, you said pebbling though. When they make the ice, they pebble the ice.
They do pebble the ice. It gets worn down every time a stone goes over a path, a track, and you sweep on that track. It gets worn down. But pebbling at the start of the game, that's always pretty rough. It was the roughness on the bottom of the stones running band.
But if they didn't pebble it,
If they didn't pebble
higher
it,
friction or lower friction?
way higher friction. Rob, if they didn't pebble it and the stone was flat on the bottom, in the extreme case, the strongest guy in the world, Magnus Magnusson, from wherever he is, he could not get a stone to the other end of the sheet. So
okay, that's great, because that's I mean, there's children's shows that talk about friction. They'll say this surface is very smooth, it has very low friction, but really friction is not always about how smooth it is. In some cases it might be, but roughness can actually make things have lower friction.
yeah,
too,
it's sort of a bathtub shaped curve, but I've always, I mean, when you have more contact area, there's going to be more friction. You're shearing more bonds. When you have less contact area, there's going to be less friction. So yeah, with the pebble, if you had flat ice, you couldn't get a stone to the other end.
Yeah, that's very interesting. That's good. Any last questions?
Yeah, I know it's lunchtime there. Sorry, guys.
Yes. Thank you so much. It's very interesting. Really appreciate it. Maybe I'll so they can see you. We could not share your screen so we can see you. Right now, you're about 2 inches.
Oh, okay. So I'm sorry, stopping my share. There. Can you see me now? All right.
Okay.
Yeah. Rob, thanks for inviting me. It was a lot of fun. You actually forced me to put this together, which I appreciate, because now I can keep working on it, and I can give it at other places and improve on it. So appreciate it.
I wonder where you got the neat shirt.
Oh, thank you. My children, actually, there's a company called Guston, and it's sort of, I want to say, a custom made shirt. Their business model is you fund it. You would choose the shirt and you pay for it. And when they get enough people buying that fabric, that design, they will make them. So I had to wait a few months, but anyway, I have another one of the bicycles on it, navy blue. It's very cool too. But the company's called Guston, Gustin. They're out of the United States, and it's sort of a crowdsource, model. You pay for your shirt in advance, and then when they get enough orders, they can make them for you. But yeah, this is my chemistry and physics shirt.
That's great. Also, just Steve visited before and gave a seminar. I don't remember when that was, but when we were starting the tribology minor, and gave a seminar to the students. So thank you, Steve, for.
Yeah, sure. Bye, guys. I'm heading off. Thank you very much, and have a great rest of your day. Rob, you're doing a great job there with the tribology minor, and keep it up.
Have a good day.